the Sioux Climate Hub. Okay. We are a member of the Climate Reality Project, which is part of the international Climate Reality Project.org. Next slide, please, Carmen. So what do? We act as a catalyst for diverse climate actions in the Sioux area. We're informed by global trends and national policy, but most importantly, we're focusing on issues and actions specifically relevant to local citizens. You can reach us on Facebook and by email at siouxclimatehub@gmail.com. Our current focus is through Facebook and this webinar series. Post-COVID, we hope to expand our public outreach. In fact, we've just had a community event that Tobin Kern organized in Bellevue Park on plant-based acknowledgements. But we hope to continue that through face-to-face events. Notably, there are no membership fees. And as a network of like-minded citizens, we need your ideas for activities, your hand in promotion and completion of those activities, and your continued encouragement of climate change awareness. Next slide, please, Carmen. So tonight's presentation is by Ted McPherson. It's about understanding methane, a significant and abundant greenhouse gas. Ted McPherson is a mechanical engineer who has worked on the Canadian space programs and later in designing optical machinery in Canada and Germany. Following retirement, he has put his engineering background to use studying the physics of climate change. As Ted notes, there are many aspects and disciplines related to climate change and many ideas regarding how to slow or stop its progress. Tonight, Ted will address one of the lesser known but most important aspects, the role of methane. Indeed, it is now widely acknowledged that cutting methane emissions may be the single fastest, most effective way to slow the rate of warming right now. And finally, at the bottom of the slide, a reminder that our next presentation will be Wednesday, September the 22nd at 7:30. Rob Keane, the CEO of Forest Ontario and Forest Recovery Canada, will present on climate change and the 50 million tree program. The recently released sixth report of the UN IPCC states that deforestation currently counts for about 30% of greenhouse gas emissions worldwide. So restoring forest is vital to reducing CO2 emissions and regulating the climate, as well as cleaning the air and water and providing important habitat for wildlife. So I now would like to ask Claudette Trudeau, who's a member of Serpent River First Nation, to do the land acknowledgement, followed immediately by Ted's presentation.
Ani, bonjour. Good morning, good afternoon, good evening, everybody. My name is Claudette Trudeau. Claudette Nadijnakas, Nabajing Donjaba, Anishinaabe Kwe, Makwadodam. My name is Claudette Trudeau. I'm from Serpent River First Nation, as Rob said. I'm Ojibwe and French Canadian, and I am Bear Clan. It's such an honor to be here today with the Sioux Climate Hub, and I encourage all of you at the moment to just reflect on the land that you're on. Right now, we are on the traditional territory of Boating, Sault Ste. Marie, the territory of the Anishinaabe, located in the Robinson-Huron Treaty Territory lands, territory of the Garden River First Nation and Batchewana First Nations, in the traditional territory of Anishinaabe. But the territory is home to many First Nations now, Inuit and Métis. We all share this land. It's so important to acknowledge the land as we begin this wonderful presentation. Looking forward to always contributing to the Sioux Climate Hub, the important environmental organization. And we are especially interested to hear from Ted today. Bindigan, welcome, Ted.
Well, thank you. And I'm going to see if I can share my screen now. Okay, can you see the shared screen?
Looks good.
Okay, good. Okay. Well, just a brief introduction to climate change, or just a very brief overview, some of the terms that we use. Basically, on the slide here, you can see that climate change starts with greenhouse gases. The greenhouse gases cause global warming, and global warming is a major cause of climate change. And climate change typically gives us more forest fires, floods, stronger hurricanes, droughts, etc. And one other aspect of climate change that is not affected with global warming is that the greenhouse gas carbon dioxide also causes ocean acidification. It makes carbon dioxide becomes carbonic acid in the ocean and makes the oceans more acidic, which can affect all of the life in the oceans. So we usually talk about climate change because this covers all aspects of the climate changes caused by man, not just the global warming, but I tend to talk about global warming and climate change very closely related. So just a simple summary of global warming. The Earth had a stable temperature without man-made greenhouse gases. And in that time, the incoming energy from the sun warmed the Earth, and the infrared radiation to space cooled the Earth. And as long as these two were in balance, the temperature of the Earth stays roughly the same, as long as they're roughly in balance. What's happened since man has come along, we've added greenhouse gases, which blocks some of the infrared radiation to space. And they have basically no effect on the solar radiation coming in. So now we have more solar radiation coming in than we have infrared radiation going out. This imbalance, more heating and not as much cooling, makes the Earth warmer. Now, adding greenhouse gases causes the Earth's temperature to increase. So how do we stop the temperature from increasing? If adding greenhouse gases causes it to increase and we want it to stop, yeah, you guessed it, we have to stop adding greenhouse gases. That's the basis of what we need to do in the next years ahead. But it isn't quite that simple either. The Earth has already warmed about 1 degree due to the greenhouse gases. And we're adding greenhouse gases every year and increasing the temperature now at about 1 degree, additional 1 degree every 50 years. Now, what happens if we could suddenly stop adding greenhouse gases today? Because that's what we want to do. We want to stop. Well, unfortunately, the global warming doesn't stop right away because we've already got greenhouse gases, additional greenhouse gases in the air, which continue to warm the Earth, even if we stop adding more. So what happens is that the temperature of the Earth will continue to increase by about 0.5 degree over the coming decades, even if we could stop right now. And eventually what happens as the Earth gets warmer, the Earth radiates more heat, and eventually you get back to a balance where the radiation out is equal to the radiation in. And we're at the point right now where there's about, that balance would happen at about 1.5 degrees Celsius. If we continue as we are this year, and we'll probably do next year and so on, if we continue adding more greenhouse gases, the temperature rise will become even bigger. And really, if we wanted to stop at 1 degree, which is where we are right now, we should have stopped adding greenhouse gases about 25 years ago. So this time lag between making a change in greenhouse gases and a change in temperature is of the order of a generation. So this is one of the problems with global warming, is that people think, oh, we should stop. But really, we should have stopped 25 years ago. Now, just a brief look over the history of carbon dioxide. We'll go to the next slide. And this shows the carbon dioxide in parts per million, starting 800,000, years before the present and going up to the present time. And what happened in the last 800,000 years is there were times like here where the carbon dioxide level was low, and that was an ice age. There were times like here where the carbon dioxide level was higher, and that was an interglacial period, a time between the ice ages. And in the 800,000 years, the highest concentration has been about 300 parts per million. And recently what's happened, you see this line here that goes almost straight up. This is the change in the last 150 years or so. And we've gone from about just under 300, about 280 parts per million to over 400 parts per million in the last, mostly in the last 50 years has been the biggest increase, but going back about 150 years. So when we talk about a temperature increase, we're going back to about the time of this red arrow here. We're going back to about the 1800s is sort of a reference. When we talk about the temperature has increased 1 degree, we're talking about the time before people's impact on the environment was large, when people had a small impact on the environment. And one little note that I would add here is they talk about the carbon dioxide levels. I've got to note that the last time the carbon dioxide levels were this high, sea levels were almost 20 meters or about 65 feet higher than today. And that's quite likely to happen. It doesn't happen right away. They're talking about a meter rise by the end of the century or something of that level, but it will continue. This is likely to continue. And this is one of the well-known effects of global warming is when the earth gets warmer, the ice melts. So now I want to talk a little bit about methane. I've got another chart here for methane. Both these charts, the carbon dioxide and the methane, are taken by scientists from measurements of ice core. They measure the air gets trapped in the ice in the Arctic and the Antarctic, and they take ice cores, measure the carbon dioxide levels, and measure the methane levels. Methane is a much smaller amounts because the first one with carbon dioxide was showing parts per million. So we're in the range of 300 parts per million. With methane here, we're looking at parts per billion. So that's billion is 1,000 million in this case. So we've got increase since since 1,000 years before the year 1,000 rather, to year 2000, we've gone from about 700 up to about 1,900. So there's been a large percentage increase in methane, but the actual amount of methane is much smaller than the amount of carbon dioxide. So carbon dioxide provides the largest share of global warming, and after carbon dioxide comes methane, which is responsible for about 23%, or say a quarter of the global warming right now. Methane composition is CH4, carbon and hydrogen, and it is produced mainly by anaerobic decay of plant material. So plant material being grasses, trees. And anaerobic is a term that scientists use, which means that there's an absence of free oxygen. So for example, if you have decay of plant material underwater, where oxygen can't get at the plant material because of the water, then you will probably get methane in addition to carbon dioxide. If you have plant material that's lying on the top of the ground where air can get at it, oxygen can get at it, then you will get carbon dioxide. That's just the way the microbes work. Now, one example, I'll just give a look at a cycle here. One example of a methane cycle is from cows or bison. We'll take bison, for example. Both cows and bison are ruminants. And that means they have an extra stomach called a rumen. So when they eat the grass, they swallow it first and it goes into the rumen and it ferments. And it's fermented in the rumen with where oxygen cannot get at it. And so it makes carbon dioxide and methane. So these gases are, the cows and the bison belch these carbon dioxide and methane out into the atmosphere. And for your typical cow, it's about 180 liters of methane and 540 liters of carbon dioxide every day. Now, if we look at bison, what happens is that there's a cycle. So we'll start here. Let's say, just for example, we have 12 tons of methane in the air. Methane breaks down in the air. It breaks down to about 1/12 of the methane will break down every year. So if we have 12 tons of methane in 1 year, we'll break down 1 ton of methane, and that breaks down into about 3 tons of carbon dioxide. The reason it's more in carbon dioxide than methane is because we're doing this by weight, and the oxygen in carbon dioxide weighs a lot more than the hydrogen in methane. And so I think it's 2.75, but I've rounded it off to 3 times. So the same carbon in carbon dioxide, the carbon dioxide weighs more than the same amount of carbon weighing methane. So we take 1 ton of methane away every year. Now, the next thing in the cycle is that we have plants. Plants remove carbon dioxide from the air, and they store it in grass or plant material. So let's say we take the 3 tons of carbon dioxide away from the air and store it in the grass. Then the next thing in the cycle is that the bison eat the grass and produce the 1 ton of methane. And so this is a cycle. As long as it's the same number of bison, the number of bison remains in balance with the methane, you get no change, because we add 1 ton of methane from the bison, we subtract 1 ton of methane because it breaks down in the air. And this is what happened over the centuries before Europeans came to North America, is that the bison were there. There was a certain amount of methane in the air because of the bison, but it was stable. It didn't really change. Now, in the long run, if we'd had twice as many bison as we actually had, you can double all these. We would go to 24 tons of methane, and twice as many bison would produce 2 tons of methane. So it scales. But this is as long as the number is reasonably in balance. The number of bison and the amount of methane in the air change slowly. So now what's happened is that the bison are gone and we have cows, and we have more cows than bison. And what's happened in the last 50 years is that beef consumption worldwide has roughly doubled in the last 50 years. And this means that roughly we get double the amount of methane from cows. So the reason for this increase is not really that a person eats more beef, that we eat more cows. It's that the world population has doubled. So the world population has doubled. We've got twice as many people to eat cows. We grow twice as many cows, and we have twice as much methane in the air compared to 50 years ago. The methane component from cows, that is. So we could reduce the methane from cows by eating less beef. If we all ate less beef, fewer cows are growing, And then the methane would not be produced by the cows and the methane would be reduced. So why would we want to reduce the methane? Well, the reason we want to reduce methane is because methane is a very strong greenhouse gas. And let's see, the next slide shows a calculation of greenhouse effect for methane. Okay, this is a slide showing carbon dioxide equivalent of methane. And the reason we talk about carbon dioxide equivalent is that carbon dioxide is the most important greenhouse gas. Most of the warming comes from carbon dioxide. But if we have methane, we want to know, how does this compare in terms of carbon dioxide? How much stronger is methane? And so we go through a calculation to calculate a carbon dioxide equivalent of methane. This is just a way of comparing the two greenhouse gases. And really, there is no simple answer. There are two effects of methane that are quite different than carbon dioxide. One effect is that methane is a much stronger greenhouse gas. So a ton of methane in the air creates something like 100 times the heating of the same weight, 1 ton of carbon dioxide. So that's one effect, is it's a lot stronger. The second effect of methane is that it decays, and it decays from a very high level down to a very low level over time. So there are two different effects, and it really isn't possible to find a number that says that the two are equal that will satisfy everybody. It depends on the time frame that you look at. But what the scientists have decided is, when they talk about the carbon dioxide equivalent of methane, we give the average over 100 years, the average amount of heating that is caused over 100 years. So what happens at the beginning? Up here, we start with something like 180. The carbon dioxide equivalent in tons is about 180. And this orange line shows that if we followed this line, in about 12 years, it would decay to nothing. So we say the lifetime of methane in the air is about 12 years. But this doesn't really mean that it's all gone in 12 years, because what happens is you get, as let's say half of it is decayed, then the rate of decay is no longer based on the original amount, but 1/12 of the new amount. And so if you follow that curve, taking 1/12 away every year, you tend to follow a curve like this, that starts off very high level, and in say 30 years, you're down to just over 1/10 of the original amount of methane. And as you go down to 100 years, what happens is the methane has turned into carbon dioxide. So all of the original methane after 100 years, or almost all of it, has turned into carbon dioxide. Now we want to know the average, the 100-year average. And here it shows that the 100-year average is about, I think it's about 28. The numbers vary. You see different numbers up around even as high as 35 for a 100-year average, depending on how much, this is for the future, depending on how much methane we put into the air. So this 100-year average is the average of the heating. So up here at the beginning, it's much higher. So up to about 28 years or something like that. In this area here, we've got a lot more heating from the methane than the 25-year average. And then in the last 70 some years, we have less heating from the methane. So what we do is we take the average of these values. And I'll just like to talk about 3 different greenhouse gases and how they differ. We'll talk about water vapor, methane, and carbon dioxide. So first of all, water vapor is actually the strongest of the greenhouse gases. It causes about 3 times as much warming as carbon dioxide. But the thing about water is that it only stays in the air about a week or two, and then it rains. So it does not stay in the air. The other thing about water is that human production is negligible. There's just enormous amount of water evaporated from the land and from the oceans, and then comes up into the clouds, into the atmosphere, forms clouds and rains. And so there's this huge cycle of water vapor, which has been going on for many, many centuries and is not very much influenced by what people do. So we don't really deal very much with water vapor. It's not a greenhouse gas that's caused by humans. What the ones we worry about caused by humans are called forcing greenhouse gases. So we have greenhouse gases like carbon dioxide and methane. The one thing about water vapor, though, is that it does change with temperature. So, for example, if carbon dioxide raises the temperature of the Earth, we will have more water vapor. And this additional water vapor will also cause additional warming. So what the scientists do when they're calculating the effect of carbon dioxide is that they include the multiplier for water vapor in the carbon dioxide and when they're calculating the amount of heating. So water vapor really never shows up as a greenhouse gas. It just amplifies the effect of other gases. And then the other two are methane, which is pretty much mentioned that. It's a very strong greenhouse gas and decays so that in about 30 years, only 1/10 of the original methane is left. And methane, I'll get the right one yet if I keep trying. Methane pretty much goes into the air. It doesn't go anywhere else. And then it decays to carbon dioxide. The carbon dioxide is a little bit different. It's a greenhouse gas that doesn't really break down. But what happens when you put a ton of carbon dioxide in the air is over a relatively short time, I'm not sure, a year or a few years, of that 1 ton of carbon dioxide, about 1/4 of it is absorbed into the oceans. And that causes the ocean acidification that I was mentioning in the previous slide. And another 1/4 is taken up by plants, because if the carbon dioxide in the air increases, plants appear to be able to take store more carbon dioxide. So 1/4 of it is added to the plants. But the remaining 50% of the carbon dioxide remains in the air for thousands of years. It's just a very long time. So what you have here on this original thing is the carbon, in this original chart, is the carbon dioxide equivalent in tons. So if you put 1 ton of methane in the air, the carbon dioxide equivalent is that you would have to put in something like 180 tons. You'd have to put in 180 tons of carbon dioxide to equal the same heating that you get from methane. Now the 175, the 180 tons that you put into the air, only about half of that remains in the air. So the other half goes 1/4 into the ocean and 1/4 into plants. So that is the calculation. The calculation is how much carbon dioxide would you need to give the same heating as the methane. And the number we use is the average heating over the 100 years. So at the beginning, it's very, very high. The heating is very, very high for methane, and then it drops down as the methane decomposes in the atmosphere. Now, just give a slide here that gives the sources of methane, the global sources of methane in an overview. We'll just look at the size of these. The red ones are man-made. It's fossil fuel use or fossil fuel production and use. Another one is agriculture and waste. I'm going to skip this one. The green ones are natural ones. So the green one is wetlands, is a natural source of methane in the air. And the other big one is the sink. That's what I was talking about, that methane breaks down into carbon dioxide. One that I didn't mention earlier is the soils. There are actually bacteria in the soils that react with methane in the air and reduce it to carbon dioxide and water as well. And I'll just give a little more detail in the next slide. This has a little more breakdown of methane sources. So the natural ones in blue are wetlands, some methane hydrates in the ocean, and termites. And those ones we don't usually count because they've been going on for centuries, and we look at mainly the changes. We look at, when we look at temperature change of 1 degree C, that's the change that we've made, and that's caused by man. And the changes that we have by man are, the biggest one right now is coal and oil and natural gas production and distribution. That's the biggest one right now. After that, there's one they call enteric fermentation. It's what they're referring to here is the cows and bison and other ruminants like sheep and goats. The next biggest one is rice cultivation. Rice cultivation is a big one because there's a lot of rice cultivated, and they do this, they flood the fields. So this is prevents the oxygen from getting at the plant material, and the rice fields produce methane. I'm not going to go into the others very much. I just want to talk a little bit now about two forms of carbon equivalent. I talked about carbon equivalent on that one slide, but let's talk about natural sources. So let's consider a natural source of methane such as wetlands. So there are huge wetlands in the shield area of Canada and other parts of the world. So human activity doesn't make much difference to the methane produced by these wetlands. And these wetlands follow a cycle similar to that of cows, except the methane is produced by decay underwater. So you have plants that produce, that take carbon dioxide out of the air. Then underwater, the plants decay and produce methane and carbon dioxide. And then in the air, the carbon dioxide or the methane decays back to carbon dioxide. So this is a cycle, and as long as you don't have very much change, there's no difference in the amount of methane in the air. So when we talk about natural sources, we usually look at this cycle, and this cycle doesn't change. So even though if we go back to this slide here, that there's a lot of methane produced from wetlands, it's a big source of methane, it hasn't changed from the 1800s and earlier. And so this doesn't really get counted in the methane budgets. But man's use, like agriculture, is changing rapidly. We keep producing more and more from agriculture, more rice fields, more cows, and our fossil fuel use has increased. So in one case, we look at, for natural sources, we look at it as a cycle which really makes no difference. And in the case of man's production of methane, we look at the 100-year average. So going back to the 1800s, so let's say, the man's use was essentially zero. Everything that we produce now is an increase from what was produced in the 1800s. If we look at the natural ones, it hasn't really changed very much. And so the natural emissions don't really affect the amount of methane in the air. It's a cycle that has a net change in the methane, which is very small. So what about the bison emissions before the Europeans came to North America? Well, that one is pretty small, and I don't think it gets counted, but on the scheme of things, it's a very, very small emission when you take the total global emissions of methane. So now I'd like to talk about some of these methane sources. I'll talk about the methane in landfills, coal, oil and gas, and cows. I'll start with landfills first. Methane is produced by waste treatment in landfills, that's garbage dumps. And garbage is dumped in a landfill, and typically the garbage is covered with a layer of dirt so that doesn't blow away, and so that to keep the animals away from it. So the air can't reach it. The decay produces methane. And some approaches to reduce the methane emissions, the greenhouse gas emissions, are flaring or burning of the methane. This stops the methane from going into the air. If you burn it, if you can capture it all and burn it, it isn't methane that goes into the air, it's carbon dioxide. So for every ton of methane burned, about 3 tons of carbon dioxide is released into the atmosphere. And this is done because over the 100-year average, you get less greenhouse emissions from the 3 tons of carbon dioxide than the 28 tons of carbon dioxide equivalent of the ton of methane. And in fact, when you burn the methane, you've got essentially a cycle, because the plant material, the cardboard boxes and all the other garbage, was produced by plants, which have taken the carbon dioxide from the air, and you're burning it and putting it back into the air. A second method of reducing the amount of greenhouse gas from landfills is to capture the methane. If you can capture the methane, you can burn that in a turbine to generate electricity, or you can burn the methane for heating. So you still get the same amount of greenhouse gases, but you get some value out of it. And the similar thing with composting. Most modern cities collect material for composting. This reduces the amount of material going to the landfill. So that's one big advantage. You don't need as big a landfill. And composting is an aerobic decay of the material. Oxygen is present, so essentially no methane is produced. So the amount of carbon dioxide produced is similar to that from flaring the methane, but the advantages of composting are that the size of the landfill is reduced. You don't have to have a space in the landfill to store all that material that you can compost. And the composted material can be used for enhancing soils or can be sold for use in enhancing soils. So the next thing I want to talk about is the oil and gas and beef. So here is a chart. And this is for Canada. This is the greenhouse gas emissions, and this is in tons of carbon dioxide equivalent per year. And I'll talk about beef first. So the average Canadian eats about 25 kilograms of beef per year. And maybe in units that are easier to understand, this is equivalent to about 5.5 Big Macs in a week. So the methane produced by the cows to grow this gives about 0.19, about 0.2 tons of carbon dioxide. So each person produces indirectly about 0.2 tons of carbon dioxide, which is the amount shown on this graph. The cows that produce the beef produce 0.2 tons of carbon dioxide. So if everybody in Canada stopped eating beef, we could kill all the cows. We wouldn't need any cows for producing beef, and we would save 0.2 tons of carbon dioxide per person. The other one I'm showing here is oil and gas, and oil and gas produces emissions. They're called fugitive emissions, and they come from things like when oil and gas are extracted, sometimes there are leaks and it just leaks into the air. Another thing is pipelines. Pipelines sometimes vent oil and gas for use in control, or they have leaks in valves. And I have two measurements. It's generally the oil and gas have been, the emissions, the methane emissions from oil and gas have been measured by the oil industry. But recent emissions, not only in Canada, but worldwide, are showing rather that emissions are higher than the industry estimates. So the industry estimate right now is about 1.5 tons per person per year. And that's just based on the fugitive emissions in 2018 were 55 million tons of carbon dioxide in Canada. You take that 50 million tons and divide it by 38 million people in Canada, and you come up with 1.5 tons per person. Then the Environment Canada did a different method of measuring the methane, and they came up with almost twice as much, which is over 2.5 tons of methane per person. So you can see, if you look carefully at these numbers, you can see that the oil and gas number is a lot bigger than the beef number. So to me, that says that if you really want to reduce emissions in Canada, the first place to start is with oil and gas. And the way to reduce oil and gas emissions in Canada is to elect a government that will put restrictions on oil and gas. The oil and gas industry isn't going to voluntarily reduce the methane emissions because they're interested in maximizing their profits. They could get more methane emission. They could stop more methane emissions. They could even sell it, but they figure out the point where the money that they get from the methane is equal to the money that they spend trying to, the money they get from selling it is equal to the money they get from extracting it. So really the only way that we're going to get reductions in oil and gas is to elect governments that are going to encourage the oil and gas industry to reduce their methane production. For example, one possibility, if it is done correctly, is a carbon tax, and there are other measures that can be taken. Now, one note on this is that I'm talking strictly here about beef. There is also dairy products like cheese and butter. Generally, kilogram for kilogram, you get about a half of a kilogram of cheese has half of the methane emissions of a kilogram of beef. So if you go completely vegan, for example, you could get a little bit more reduction than what I've shown on this chart. Now, the next thing I would like to talk about is methane for heating and methane for gas plants. First thing is methane for heating. So many of us use natural gas to heat our homes. Natural gas is mostly methane. It's about 95%. So when you talk about natural gas, you might just as well say methane. We burn it, and the products produced are water and carbon dioxide. So the natural gas, even though it's methane in your house, doesn't produce methane in the air. You don't release it into the air, you burn it, and it produces carbon dioxide. Now, I looked at the numbers for our house. It's heated with methane. This costs about $400 per year for the gas, the methane, the natural gas. If we switch to electric heating, we could heat the house for about, about $2,200 a year. So we would spend about $1,800 more. And in terms of a carbon tax, if we had a carbon tax on the methane at about $700 per ton, it would pay us to switch to to electric rather, from gas. But this is a very, very large tax. It shows that it's really quite difficult to switch over economically. It's quite difficult, and there would be other options such as improved insulation, a heat pump, a smaller house. It's really quite difficult to get away from gas, and there are many other things that could be done more easily. And another note that I've got here is our family's greenhouse gas emissions from burning methane in our furnace are less than our share of Canada's fugitive emissions. So it's somewhere in between what we have from beef eating and what we have from fugitive emissions. Fugitive emissions are the biggest. Now I'd like to talk about gas plants. This is burning methane in gas plants. And in different plants, different ways of producing electricity. I've got a chart here that shows roughly the amount of greenhouse gas that's produced for different methods of generating electricity. The worst one is coal. The next one is natural gas, biomass, and then after that we get down to ones that are really very small. Any of the solar, photovoltaic, geothermal, hydropower, nuclear, wind are all extremely low in terms of greenhouse gases. So coal is the worst, but natural gas isn't an awful lot better. And there may be new gas plants that can produce electricity with a little bit less greenhouse gas generation, they use less fuel to produce the same amount of electricity. But when we look at the fugitive emissions that go into it, it may even be bigger. So it's we're about 60%. And remember in the first slide, I said if we want to get emissions down to zero, reducing by 40% is not a very good step to be taking. We would be much, much better off with one of the other options, the solar, the hydropower, nuclear, wind. Oops. Now I want to talk another thing about heating a house and producing electricity in a gas plant. Excuse me. So I want to suppose that we have electric energy from water, hydro energy, which can be used to replace methane in either heating a house or producing electricity in a gas plant. Where should we replace the methane? Well, the answer is that we should do it in the gas plant. And the reason is because of the way electricity is generated. To generate electricity with methane, first the methane is burned to produce heat. And then the hot air goes through a turbine. And to produce 1 unit of electricity requires 3 units of heating from methane. 2 units go to heat that is exhausted to the air, and 1 unit of electricity is generated. And this is the case with any engine that's used to generate work out of heat. There's a limit on the efficiency that you can get. For example, your car. Your car is also produces energy, and what you do there is you start with heat. You burn the gasoline, and then you run it through the engine, and it takes, in that case, it takes about 4 units. 3 units are exhausted to the heat exhausted to the air through the radiator of your car, and 1 unit goes to powering the car. But back to the methane plant. So the 1 unit of hydroelectricity can replace 3 units of methane in the gas plant. 1 that goes to produce the electricity, the same amount of electricity, and 2 units that go into the air, heating the air. In home heating, it's pretty much 1-to-1, because we're not looking for work there, we're looking for heat. And when you burn it in a furnace, you can get a furnace that's pretty close to 100%. I have a furnace that's 95%, and the new ones I think are 98%. So if you're using hydro, where should you put the hydro to use? Well, you should reduce the gas plant, because you save 3 times as much greenhouse gases compared to using it for home heating. And the final thing I want to mention is the gas plants in Ontario. The Ontario government and the Ontario Electric Generating Group, I forget the name of them, they have a plan to greatly increase the use of gas plants, methane plants, in other words, for electric generation in Ontario. The reason is that the Pickering nuclear plant has reached the end of its life and will be shut down, and other nuclear plants require maintenance, so they'll be shut down for maintenance as well. And the plan is to replace this lost electricity with electricity generated by gas plants. This will increase the greenhouse gas emissions by about 10 million tons. So that's about 3/4 of a ton per person in Ontario. It's more than 3 times the methane emission from cows to produce beef. Now, there are better options. Quebec has offered to sell hydroelectricity to Ontario at 5 cents per kilowatt hour. Wind power would be a cheap option for part of the power, except that the government has recently spent about $230 million to cancel contracts for renewable power and tear down partly finished wind turbines. So when the the person running the electric, or the group running the decisions on electricity, look at the options for wind turbines, they can't buy any from wind turbines because we just tore a bunch of them down. And Ontario also purchased a number of gas plants. So the government of Ontario, the government that we have right now, is very, very strongly against renewable energy and in favor of fossil fuels. So this again shows you something that I was saying before. If you want to get things changed in terms of greenhouse gas emissions, you can make little changes yourself. But in many, many cases, you've got to get governments. You've got to get the right government to make the change. And it's not just the government of Ontario either. If you look at the cost of the emissions, or cost of the, the cost of the electricity, we really should be factoring in the carbon tax into the cost of the electricity. Once you factor in the carbon tax, all of a sudden the hydropower from Quebec is cheaper than the gas plants. But the Ontario government asked to not include the carbon tax on gas plants, and the federal government has agreed, okay, we won't put a carbon tax on the gas plants, or we make it very, very small. So while a carbon tax is a good thing to have, it's one good way, it's not necessarily the best, I don't want to get into that argument, but it's a good way to do it, provided that you put the carbon tax on all the emissions. You can't say, well, Bill and Joe, you have to pay a carbon tax on everything you do, but Doug, you don't have to pay the carbon tax. That sort of approach is a bad one. So again, this shows the importance of electing governments with good plans for the environment. And the average citizen has no choice about where you get your electricity. So the Ontario Clean Air Alliance, if you go on the website for the Ontario Clean Air Alliance, you can find a lot more information about gas plants in Ontario. So that's just about all. I've run up past my time, I think. Just a quick summary. To stop climate change, we need to stop adding greenhouse gases. And if we stop today, the global temperature increase would be about 1.5 degrees. We should have stopped 25 years ago to keep down to 1 degree, but that's just the way the physics of the thing works. You can reduce greenhouse gas emissions by reducing beef and dairy consumption, and that's a good thing to do. I'm not saying that it's bad. It's definitely a good thing. It's a good one, something you can do, and you can see well, you can't see it, but it will make a difference. But the more important thing is you've got to elect good governments. And gas plants for electricity, while they're slightly better than coal plants, but the carbon dioxide emissions from gas plants are far too high. The Ontario plan to increase the emissions from gas plants is very bad for the climate. And so that's the end of my discussion. And I would take questions. Anybody have any questions? I'll have a look in the chat. That's this one. Moving to power production not based on coal or gas is indeed the right way to go. However, we should we not also factor in the production of the materials? Well, that chart that I was showing for the materials, it shows a non-zero value for windmills and all of the others, which is intended to, which shows the production costs. So I think that is factored in. If you just took the, if you don't count the production of the materials, then you would get essentially a zero cost for wind energy, and the same thing for hydro. And you say, so large industrial production like steel needs alternatives to coal and gas in a major way to produce products for greenhouse gas reduction. Can this be done? Yes, there are alternative solutions, but I don't think it's an easy one either in steel. The easy ones are right now are electricity and electricity production, automobile or transportation, where we can go to electric vehicles, and of course the corresponding reduction you get there from oil and gas. And in addition, the oil and gas can go to production methods that reduce the emissions from production. So about 30% of the emissions in oil and gas are in the production of the oil and gas, not just from the burning of it. So we can improve that as well. Next question. I've read that one of the problematic aspects of increasing hydro dams is the increasing methane. No, I'm sorry, I don't know an answer to that one. I guess what they're saying is that you're flooding the area, and that would make sense, that when you flood an area, then the trees and the plants that are there are going to be covered with water, and more methane would be produced. I don't know how big that is. Any other questions? Anybody want to unmute themselves and ask a question? I'd be happy to try to answer.
Yeah, Ted, it's Rob. I'm wondering if you could comment on the impact of permafrost melting on methane production in peatlands.
Yeah, that's a good question. I didn't include that one because I can't really get a good number on it. The number in that slide that I showed, let's see, it was quite the amount that's produced now. Where was it? Other natural emissions, permafrost and vegetation was significantly smaller than the wetlands. So it doesn't seem like there's a huge amount right now, but on the other hand, the amount of carbon that is stored in permafrost is considerably larger than the amount of carbon dioxide in the air. So there is the potential there to more than double the amount of carbon dioxide. What happens is the Earth gets warmer, the permafrost melts, and you get a combination of carbon decay. You get a decay of the vegetable material in the permafrost. Part of it goes into carbon dioxide, part of it goes into methane. And so it produces a positive feedback, which could be huge. I didn't really discuss this because I couldn't really get a good number for it, but it has the potential for being a real problem for stopping global warming, because if you stop adding greenhouse gases from fossil fuels, for example, but the Arctic continues to warm, you will get some emissions from the permafrost. And I can't get a good reading on it, just how bad the problem is. I think that too, that there are a lot of things that the scientists really don't have a good understanding how bad they are. Scientists are clearly telling us that global warming, climate change is a big problem, but there's an awful lot of research going into finding out just how big it is. That answer your question, Rob?
That's good.
Not really.
Well, no, that was an excellent answer, and I think admitting to things we're not sure about is really important, because there is a lot of uncertainty there. And as you suggested, there could be huge impacts. We're not really sure, but that's very important to consider going forward. I'm just wondering, are there any other questions for Ted? And if not, I'd like to really thank Ted for a very thoughtful presentation. He's put a lot of work into that, and some very interesting slides. I'd also like to remind people that our next webinar will be on Wednesday, September the 22nd at 7:30. Rob Keane, the CEO of Forest Ontario and Forest Recovery Canada, will talk about forests, climate change, and the 50 million tree program. And just to remind you, you have to go on to Eventbrite and register for the event in order to get access. Thank you.